So continuing on with bivariate data, analyzing bivariate data or relationship between two variables, okay, an explanatory variable and a response variable. We talked about how to describe it using a scatter plot. We talked about how we take a scatter plot and we put a least squares regression line on it. And that least squares regression line is placed so that the sum of the squares, the sum of the difference of the sum of the squares of the residuals is as small as possible. Okay. And then we also we talked about how to analyze using certain factors like the direction of the relationship, the strength of the relationship, whether it's linear or not, and whether there are any outliers. So we're going to kind of focus on sort of how good the line is, and also whether a straight line would fit the data, or maybe a curved line would be better instead. We're not going to study curved lines, we're only going to study the straight lines. Okay, so I talked about residuals in the previous lesson, and it's the difference between the actual value and the one that's predicted by the least squares regression line. Okay. So this is just refreshing your memory. Between the actual value and the predicted value that we get from the line. And that's something that you're going to have to commit to memory, that little formula. So going back to that example we did in the last lesson with the percent attendance and raw score on an Algebra 1 test, I believe, a state test, I believe it was. Okay. We looked at we got 11 data values. So from those 11 data values, we put them on a scatter plot, and we were able to determine a least squares regression line that had the equation predicted value equals negative 7.69, which is the y-intercept, plus 0.57x. 0.57 is the slope. Don't confuse slope with correlation. Okay? Like a 0.57 slope does not mean that the correlation coefficient is 0.57. They're two different things. Okay? So a new student comes to the school. If his attendance rate is 80%, what's his predicted test score? Well, we can do it two ways. We can use a graph and get an estimate. So 80% is here. And if we go up to the least squares regression line and then go across, looks like we're around 37, between 37 and 38. So from the graph, we're looking at approximately 37. But if we did it algebraically, by using the least squares regression line, the predicted value would be negative 7.69 plus 0.57 times the percent attendance, which we're told is 80. And we calculate that, we get 37.91, so we're actually a little closer to 38. Obviously, if you've got the equation of the least squares regression line, you'd want to use that over the graph because it'd be more accurate. Now this student, remember, this is what they're predicted to get, but they wrote the exam and they actually got 44. So what we want to do is we want to calculate the residual or the prediction error. So to do that, we have to take their actual score minus their predicted score, right? Actual minus predicted. And we're going to get 6.09. And because it's positive, that tells us that the actual score is 6.09 above the predicted. Okay. So it's pretty straightforward to calculate a residual. And remember, just like we've been doing with all these other measures, all these other things we've been finding, we always want to interpret them, not just find the answer and stop. Now you can actually graph residuals. And they're good to graph because they tell us, a residual plot will tell us if a line is a good fit for the data in the scatter plot. And to do that, you can see a couple of examples here where we have X values and Y values. If we look at the dots themselves, just sort of ignore the line for the time being, it does look like it forms a linear pattern. Okay. And we're able to write a pretty, we're able to place a pretty good least squares regression line on there. If you took all the residuals, right? So if you took all the X values and found the residuals of each, it would look like this. Notice that the residuals are scattered all over the place. Some are high, some are low, okay, depending on the X values. But if you look at this next one, looking at the original scatter plot, ignore the line for a second, you can see actually that it, well, I don't know if a line's really that good because it kind of forms a curve. So maybe a line is not the best fit. Well, how do we know if a line's not the best fit? Do a residual plot or a residual graph. And notice the residual forms a curved pattern. So if you want to see if a line works better than a curve for your data, you look at the residual plot. If all the residuals are scattered about randomly, line's a good fit. If it forms some type of curve pattern, line is not a good fit. We should go back and we should do a curve, which we're not going to do in this course. We're just going to stick to lines. Okay. So this one, yes, because residual values are randomly scattered. It doesn't form any kind of pattern. This one is no, because residuals, remember, we're looking at the residual plot. Residuals form a curve. So remember, we've already talked about using the correlation coefficient to talk about the direction of a line and the strength of a line. And we can use residual plots to talk about the linearity of a line, or like whether a linear model is appropriate. Okay. Remember, we talked about dots. So we've addressed direction, form, and strength. Okay. This is a pretty heavy page, this next one. So basically, it's an example that we're going to talk about how good is a line. How good does it fit? Okay. And there's a couple of measures that we're going to talk about. And we're going to use this example to talk about them. All right. So after 2020, okay, Many colleges dropped the SAT, ACT testing requirements. Now, many colleges are sort of bringing them back, so they're being used more and more. And we've got some data from the University of California, which uses SAT scores, SAT scores, and also uses high school average or high school grade point average. That's what GPA stands for. And the reason that they want these values is they think that they can use these to predict how well will a student do at the university. Okay. So this is just 5 students out of 1,000 that were done in a simulation. Right? And we came up with 3 different graphs. This refers to their high school GPA and how they did in college, their college GPA. This second one talked about their SAT score and how they did in college, their college GPA. This combined their high school and SAT score and compared it to how well they did in college. So basically we want to see, is it this high school GPA is a good predictor? Or is the SAT score a good predictor? Or is a combination of the both the best predictor? Which one's the best? Okay. What do you think just by looking at these 3 scats? I know it looks a little crazy. What do you think might be the best predictor and why? Look at the points compared to the least squares regression lines for each. Why do you say both? Yeah. I mean, we can see that if we look at this one, we've got a fair number that are below, that are significantly below. This is a little better, but still below. But this seems to be more half and half. So just sort of eyeballing it, it seems like this is a good one. So composite score which consists of high school GPA and SAT. Seems to be the best line and therefore predictor of college or university GPA. But we want to be a little bit more accurate than just eyeball. So statisticians have come up with 2 measures that sort of talk about or that measure. Anybody need that stuff? Sorry. Wait for a second. Good. Okay. So how well does the line work? In other words, how good will the predictions be? Okay. So like I said, instead of eyeballing it, we've got 2 measures. One is called little s, and it's a word that, or a phrase that you're familiar with. We find the standard deviation of the residuals. Now, perhaps you can come up with a definition of that by thinking about what standard deviation means and what residuals are. What were the phrases, or what phrase did I say you should think about when you hear standard deviation? Sorry? Okay, how far? I used a specific phrase, 2 words. Typically, or typical distance, or typically varies. Good. So instead of from the mean, though, it's from the line. So the standard deviation of the residuals is the typical error. And error means basically the same thing as distance between the data points and the least squares regression line. So it's very similar, except now we're talking about 2 variable data here. What would be better, a higher standard deviation of the residuals or lower? That would make the line a good fit. Lower, the lower. So here you can see in graph A, just 5 data values, very low residuals. Okay, so which means a stronger correlation, S is lower. The second one, not bad, but the residuals, if you count them all up, will be higher. And that results in a weaker correlation. And this is kind of a sentence you can use when you're asked to interpret the standard deviation of the residuals. Okay? We're not going to worry about how to calculate S. We're going to focus on how to interpret it. So here, we're back to our high school state test example. We've calculated the residuals. From that, S has been calculated, and it works out to 1.99. So you can sort of write it like this, or you can just say the typical, like I can phrase it a little bit differently. No, actually, you know what? I'll stick to this script. So when using the least squares regression line, and just do that. I love it. When using the least squares regression line, with percent attendance, to predict test score. We will typically be off 1.99, and there's really no units for this one because it's a test score. It's a raw test score. It's not a percent. Okay. So 1.99, I mean, I guess I would just put units. If the units don't look obvious, just put units. So going back to the example we did on the last page, using the 3 different ways to try and predict college GPA, you can see that if the standard deviations of the residuals are calculated, the lowest one is in fact the composite score. So that tells us here, because this is lower than this and this, not by much, but it's still lower. This tells us that this would probably be the best predictor. So we can be a little bit more accurate in saying that rather than just eyeball, because we've got an actual measure that we can use. Okay. So we would just say, why it keeps doing it. Drives me crazy. So composite score. Because it has the lowest S value. So it's kind of it makes an argument for bringing back SAT and ACT scores because those scores, those standardized tests, along with how well you do in high school, seem to be the best predictor. Okay. Notice that high school GPA was the worst predictor. Why do you think that is? Just out of curiosity.
High school university are different.
Yes, how?
Well, harder. Their grades are expected to drop as more university.
Yeah. And that's sort of that's an argument that many people make in education is that marks are too inflated in high school. So they say that high school should be harder. And it should be more demanding instead of an average of 85 to 90 on tests, the averages should be 70 to 75. Okay. I know your feelings on it. You don't have to tell me your feelings. Or make university easier. That's one way that they can do it too. Okay. I don't know. It's hard to say. I mean, like I can make an argument that high school is perhaps too easy when I compare how well you guys do in grade 12 pre-calc on your tests compared to how well you do in the provincial exam. But the thing is, which one's the best? It's hard to say.
Sometimes if like the average basically one like 70 comparison be like harder, then when students subscribe like the average down where it is.
Yeah, could be. And the other issue is that universities have actually started to change, and they've made their admission requirements higher. Like before, you could get in, into say McGill science, which only looks at your marks. They don't look at anything else. McGill only looks at your marks. Like the average to get into science could have been 85 at one time, but the high school marks went up so high that they had to raise the average. Now, to get into McGill science, you're looking at an average of 95. Like that's crazy, right? But they refuse. They say no, marks only. Whereas a lot of other universities, they said, okay, we can't just do marks only. We got to do something else. So we want to see what you do outside the classroom. So you give those, you answer, like the UBC gets you to answer a bunch of questions in addition to your high school transcript. Queens does the same thing. McMaster, you have to write, you have to write an essay on a really weird question. Yeah, they come up with weird questions every year. So anyway, something interesting. Okay. The second measure of how good a line is, how well it predicts, is something called the coefficient of determination, and we label it R squared, and it actually relates to correlation R. It's taking the correlation R and squaring it, okay? And that R squared is a good measure of telling us how good the line is, how well it predicts. So we did this way back in the first lesson. Well, I guess not way back. What's that? So if I give you all these and square them all, I'm going to get this. Okay? All I did was square the r's. And notice that they all become positive. So r squared is always going to be a positive value. So the question now becomes, is a higher r squared better or is a lower r squared better? Well, r squared has to be between 0 and 1, right? Because correlation has to be between -1 and 1. And when you square those, you get 1 and 1, or you could get below 1, but greater than 0. If it's perfect, r squared is 1. If there's no correlation, r squared is 0. So obviously, the higher r squared is, the better. So it's the reverse of the standard deviation of the residuals. The higher, the better. So the closer it is to 1, the stronger the correlation is. Yeah.
And what is it?
It's measuring the strength and the direction of the line. That's what we did in the first lesson. R measures strength and direct, and then r squared will measure how good is the line. Okay. So r strength. That's a good point of that. And direction. And it can be positive or negative between -1 and 1 inclusive. But r squared, for lack of a better phrase, how good the line is. So if you calculate r, if you know what r is, then you can calculate, then you know the strength and the direction of the line, and then you just have to square it to find how good the line is. If you know r squared, you know how good the line is, and then you just have to square root it to find the strength and direction of the line. So as r squared is closer to 0, it's a weaker correlation. And if r squared is closer to 1, it's a stronger correlation. It's a better predictor. So if all the points fit exactly on the line, like you see there, r squared is 1 or 100%. That means that the line completely explains the data. As it starts to go down, okay, the line can be still good predictor, but not as great as it would if it was higher. And the lower it gets, the worse predictor it is. Okay? So if it's, say, 0.72 or 72%, we would explain, we could say it explains most of the data. So what does that mean? That means that there's some other things there that are explaining the data too, some other variables that are going on. Okay. And here's your stem for how you can interpret r squared. And notice we say percent. Okay. So we would say whatever r squared is, of the variation, whatever the response variable is, can be explained by the linear relationship with the explanatory variable. So if we go back here to our GPA SAT, we can see it makes sense that r squared will be highest with the composite score. But still, it's not great, is it? I mean, it's 26%. So 26% of the variation in the data values can be explained by this line, but the remaining percent has to be explained by some other factors. So what could it be? What do you think? What are some other factors that could influence how well you do in college or university? What's that? Attendance? Sure. Time spent? Yes. What about family income? Could that play a factor? Yeah, could play a factor. I mean, maybe, you know, you got more family income, you've got more money to spend on tutoring and things like that. Okay, so other factors come into play. So for this one, we would say 26% of the variation in college GPA I got the stem right, can be explained by the linear relationship with composite source. So again, these stems, I tried to sort of get you to understand what S and R squared mean. And hopefully not just, you guys okay? We all right? Okay, something fascinating out there? What? What's fascinating?
I'm watching them. Yeah. They're like seeing us in Mars. Yeah, I'm looking at it.
What?
Yeah. Things going to the last one.
All right. We got this? Yeah or no? No, because you're looking at outside.
Focus right here.
Better than yawning, I guess. Did I know you were a lefty?
Yeah, I have lefty. Lefty too.
Yeah.
Oh, really?
Yes, really. Okay, ready?
Almost.
Uh-huh. Kelly? Yes? Okay. So here, just to answer this question, and we're just comparing back to this. Does adding SAT scores make the predictions better? Yeah, it does. It's twice as much in percent. Okay. Whereas if it's just high school, it's only 13%. If it's high school and SAT, it doubles to 26%. So we would want to say yes. Because R squared doubles. Percent to 26% when we include SAT scores. Okay, so we talked about the strength of linear relationships. We talked about the direction of linear relationships. We talked about whether linear is a good model to use to represent a relationship. The last component were outliers. So my questions to you look at all the circled ones on each of the scatter plots. Would you consider them all outliers? Would you consider one of them, or two of them, or all three of them not outliers? What about A? No, because if we extended the line, we would think it would go like that. We can't be absolutely sure. Okay. So, I mean, we would say, actually, I'm going to say likely no. That's the data value. Almost. For mine. How about the next one? Yeah, likely yes. How would you explain why? Use your stats terminology. Yeah, it has a negative residual, but it has a very, I guess we would say, very low negative residual, because the higher the negative value, the lower the actual value is. So likely yes. Okay. We'll just say greater residual value. Than the others. How about the last one? No, because it doesn't really stand out. I mean, yeah, maybe it has the greatest residual value of all six of them, but how much? Likely no. Because its residual value not much different than the others. So if we talk about residual, or sorry, outliers. Okay. What effect does it have on these measures that we've been looking at in this unit? Specifically R squared, and S. Okay. Now, I don't expect you to give me exact values, but you should be able to tell me whether each one of them are going to be higher or lower. So here we have a pretty strong, moderately strong negative relationship between the X value and the corresponding Y value, because R is negative 0.79. R squared, 62, that means 62% can be explained, 62% of the relationship can be explained by the line, okay, which is pretty good. And standard deviation, 1.31, well, that's harder to tell. I mean, I don't really know, is that good? Is that okay? Is that really good? I don't know. What do you think is going to happen to R if we introduce this outlier? It's going to get closer to zero, right? Because it's probably going to pull it up a little bit like this, okay? So this is going to, I guess we would say, increase. And actually it becomes negative 0.61. What about R squared? It's going to get smaller, right? Which, when you square this, you're gonna get 0.37. So only 37% of the variation between these two variables can be explained by the linear relationship. What about S? It's gonna get a little greater. And the fact it goes to 1.85. Good. So that's what you should be familiar with to see the relationship like that. So we can say, just going to finish this off, each value changed significantly when the outlier was introduced. To finish off this unit, which we'll do next week, we actually also want to see what effect does an outlier have on the slope of the linear regression line, as well as the y-intercept. Okay. And it's kind of common sense. You can see it'll change the slope of the line. It'll change the y-intercept. Like this is probably going to pull up a little bit, which means the slope is going to get smaller. Okay. Yeah. But we'll talk about that next.
If I were to tell you like what to on a test for explaining the line.
Yeah.
And I would say like it's smaller negative value, let's say.
The smaller negative value means a better relation, means a stronger
Yeah.
relationship.
Want us to be
Well, you should be. Or just avoid using that altogether. You know, you would just say it's a stronger relationship, or it's a stronger correlation. And or it's a lower R squared value. Okay. Yes, it was, that was